Every year, billions of dollars are spent worldwide on developing military technologies. But only one aircraft has become a true ghost in the sky, as invisible as death itself. Its creation cost over $23 billion, united more than 40,000 people from 46 states, and even required the construction of a new industrial city. If you found out what is hidden under its black coating, you would never look at aviation the same way again. Does your country participate in the production of components for military aviation? Let us know in the comments. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the US Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided minimal radar cross-section and significantly better flight technical characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in the first flight and a $1 billion increase in the program's cost. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988, at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the US Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B-2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B-2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the US were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft for numerous composite elements, Hughes for radar systems, and General Electric for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B-2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B-2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B-2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B-2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B-2 Spirit is a true engineering feat that unfolded in huge hangars specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B-2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests, static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the US Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The US Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing. Did you know that over 100 million AK-47 Patton rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is FIAES, stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by SICS. Forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining crudelties, precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer and then added to the metal assembly. The final stage is Karblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the disc is formed into a primary casing. Still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length. A groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a .45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection by eye through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase. Packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. Every year, over 9 million tons of copper scrap are recycled worldwide. That's enough to build 1,800 statues of liberty. But where do old cables, transformers, and copper wires go after disposal? What do they do with them in the heart of factories where temperatures exceed 2,000 degrees Fahrenheit? And why can recycling 1 pound of copper save as much energy as a whole house needs? If you watch until the end, you'll learn a secret you've never heard before. So, in what city did you last see a copper factory? Write it in the comments. It's interesting to check the geography. It all starts at the huge warehouses of recycling plants. Thousands of pounds of various copper scrap flock here. Thick power cables from industrial sites lie next to thin wires from household appliances. Old transformers are neighbors with remnants of construction wiring. Each element has its own story, but they all share one thing. They are ready for a new life. The first stage of recycling is careful sorting. Experienced specialists separate the scrap by type and degree of contamination. Clean copper wire is separated from insulated cables. Thick industrial cables are separated from thin household wires. This is a critically important step, as different types of scrap require different approaches to recycling. The next stage is mechanical cleaning, a true art of modern technology. Powerful shredding machines cut the cables into fragments 2 or 3 inches long. Special separators use the difference in material density, as copper is heavier than plastic and rubber, making it easy to separate. vibrating tables and air currents finally clean the copper fragments of insulation remnants. The output is relatively clean copper pieces, but this is just the beginning. The real magic begins in the melting shop. Huge induction furnaces heat the copper to a temperature of over 1,984 degrees Fahrenheit, the melting point of copper. The metal fragments gradually turn into a red-hot, almost golden liquid. This sight is always impressive. Hard, cold pieces of metal become a living, pulsating mass. But temperature is just a tool. The main action happens at the molecular level. During melting, impurities behave differently. Some float to the surface as slag, others dissolve. Master metallurgists carefully control the process, skimming off the slag and adding special substances called fluxes, which help remove unwanted elements. The first refining is complete, but this is not the end. The molten copper is poured into special baths for electrolytic purification. This is the most precise stage of the entire process. An electric current of several thousand volts is passed through the melt. Under its influence, residual impurities, iron, nickel, zinc, lead, migrate to the electrodes and are removed from the melt. Electrolysis lasts for several hours. The temperature is strictly controlled between 2,100 and 2,200 degrees Fahrenheit, and the current strength is regulated with an accuracy of tenths of an ampere. Laboratory analyses are conducted every 30 minutes. Chemists check the metal's composition, tracking how the amount of impurities decreases. Gradually, the purity of the copper increases: 95%, 97, 98, 99. And finally, the coveted mark of 99.9% is reached. The purified copper is ready for forming. The molten metal is poured into special molds, ingot molds. The molds are preheated to a temperature of about 1,800 degrees Fahrenheit to avoid thermal shock. Slow, controlled cooling allows the copper to crystallize with the correct structure. Perfectly uniform ingots weighing from 50 to 100 pounds or cylindrical billets 6 or 8 inches in diameter are formed. These billets are the basis for future cables. They go to the wire drawing shop where the next transformation takes place. A wire drawing machine is a series of successively arranged dies, openings of different diameters. The billet passes through the first opening, about 3 inches in diameter, then through a smaller one of 2 inches, then 1.5 inches. With each pass, the diameter decreases and the length increases. The drawing process requires enormous effort. Powerful electric motors with up to 500 horsepower pull the copper through the dies with a force of tens of tons. The metal deforms but does not break because copper is plastic and can withstand such a load. Gradually, the thick billet turns into a thin, flexible wire with a diameter from 1/2 inch to even thinner. Each stage of drawing is strictly controlled. The diameter is measured by laser devices. The feed speed can reach 100 feet per minute and is automatically regulated. If defects appear, such as scratches, irregularities, or cracks, the process is stopped for correction. The finished wire undergoes a final quality control. Not only the geometry is checked, but also the electrical properties. The resistance must not exceed a certain value per 1,000 feet of length. Conductivity, mechanical tensile strength. All parameters must comply with strict American Society for Testing and Materials standards. After all, this wire will become the basis for cables that will transmit electricity to homes, offices, and factories. The final stage is the manufacturing of the finished cable. Copper wires are covered with insulation up to 1/10 of an inch thick, polyethylene, polyvinyl chloride, or other modern materials. Depending on the purpose, the wires can be twisted into the required configuration. Power cables for 120 or 240 volts, information cables of category 5 or 6, special purpose cables, each has its unique design. Packaging the finished product is the final touch. Cables are neatly wound onto spools, 3 or 4 feet in diameter, or placed in boxes of standard sizes. Each unit is marked, indicating the length in feet, the cross-section in American wire gauge, and technical specifications. Underwriters' laboratory certificates confirm that the product meets all American safety standards. The result of this complex technological symphony is impressive. From scrap that seemed like useless junk high-quality cable is born. It is ready to serve for 25 or 30 years, providing reliable transmission of electrical energy from residential buildings to large industrial complexes. But this is not just a technological process. It is a philosophy of sustainable development in action. Every ton of recycled copper is a ton that does not have to be mined from the Earth's depths. It means conserved natural resources, less environmental impact, and a cleaner environment for future generations. Recycling 1 ton of copper saves about 2.5 tons of ore. The cycle is complete, but it is endless. When, decades from now, this new cable becomes obsolete again, it will return here to begin a new journey of transformation. Copper is the metal of eternity, which can be recycled an infinite number of times without loss of quality. And in this lies its true value. The production figures are staggering. Over 9 million tons of copper scrap are recycled annually worldwide. This is equivalent to the weight of 1,800 statues of liberty. In America, the average family uses about 280 pounds of copper in their home, from electrical wiring to plumbing pipes. 1 million pounds of recycled copper saves enough energy to power 1,000 homes for a year. This is 85% less energy than is needed to mine new copper from ore. Recycling also reduces carbon dioxide emissions by 65% compared to primary production. The largest amount of copper scrap comes from the construction industry. That's 31%, from electronics 21%, and from the automotive industry 12%. 1 pound of copper wire can be drawn to a length sufficient to wrap around a football field 23 times. Modern factories can process up to 400 tons of copper scrap per day, producing wire with a total length of over 50,000 miles. Over the last decade, the price of copper scrap has increased by 180%, making its recycling extremely profitable. Today, recycling provides 40% of the world's copper needs, and this figure continues to grow. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, -321 degrees Fahrenheit. 1 sip and you lose part of your stomach. 1 breath and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool? Never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Every year, people throw out 4.4 billion pounds of washing machines. That is like 200 Eiffel Towers made of metal and plastic. But what if your old washer could snag you $200 from Samsung or LG, and then come back to life in a totally new way? In this video, we are going to show you how shredders rip steel apart in seconds, magnets snatch out copper, and plastic gets transformed into new gadgets. Why are brands willing to pay for your old junk? And how can a single machine either help save the planet or end up poisoning it? The first 30 seconds will spill a secret that is going to change the way you think about trash forever. You do not want to miss it. Lots of big brands and electronic stores have programs where you can trade in your old stuff, or they will haul away your old appliance for free when you purchase a new one. For instance, in the United States, companies like Whirlpool, LG, and Samsung have programs like this. Over in Europe, they have initiatives under the Waste Electrical and Electronic Equipment Directive. The details can be different depending on the company. Some will just haul away your old appliance, while others might give you a discount toward your new purchase. Whirlpool in the United States, for example, might offer anywhere from $50 to $100 off a new appliance if you are trading in an old washing machine. LG and Samsung sometimes run special promotions where they might offer $100 or even $200 back. Over in Europe, some programs might let you get up to a 10% discount on a new appliance. But more often than not, the discounts are not that big. Most companies really look at this as more of an environmental effort, not just a strategy to pull in customers. In a lot of cities, you will find electronic waste collection centers where people can drop off their old washing machines themselves. These centers often team up with local city governments or private recycling companies. In some countries, like Germany, the United Kingdom, and the United States, there are city-run services that will actually come and pick up bulky electronic appliances. For example, in New York City, you can schedule a free pickup through the city's own program called NYC Safe Disposal. There are also some companies that focus specifically on recycling metals. They might actually buy your old washing machine from you, or at least take it off your hands for free. These companies then send the appliances off to be taken apart, where they pull out all the valuable stuff like metal, electronics, and plastic. First things first, the machines get sorted into different groups. Ones that still work, ones that kind of work, and ones that are completely broken. The machines that still work might get fixed up and resold, but the ones that are too far gone head off to be taken apart. The teardown process starts by taking off the outside panels, the door, and the drum. Things like motors, electronic components, wiring, and pumps are separated out because they can often be reused as parts or melted down for their materials. The different types of metal get sorted separately, like stainless steel, aluminum, and copper. Plastic parts are also gathered up and sent off for recycling. This whole process can be done by hand, or it can happen on special automated lines where machines shred the main body and then use things like magnets and air separators to sort out the different materials. These automated recycling lines for washing machines usually involve several steps, and each step is designed to separate out specific types of materials. First, the washing machines are loaded onto a conveyor belt that feeds them into powerful rotating shredders. The blades on these shredders are strong enough to rip through the metal and plastic bodies, breaking them down into pieces roughly 1 to 4 inches across. Once everything is shredded up, the mix of materials moves past magnetic separators. These magnets grab onto any metals that are attracted to magnets, like steel and cast iron, pulling them away from all the other stuff. Next up is something called an eddy current separator. It uses a different kind of magnetic field to actually push away the non-ferrous metals, things like aluminum and copper. Plastics and other lightweight materials get separated out using air separators. Basically, strong blasts of air blow the lighter bits, like plastic flakes, upwards and into collection bins, while the heavier stuff stays put on the conveyor belt. Toward the end of the sorting line, whatever materials are left might go through optical scanners. These scanners can analyze what the pieces are made of and sort them even further, sending them to the right place for more processing or final disposal. So, after all this sorting with air separators and optical scanners, the different materials head off to their own separate processing lines. This is where the plastic, metal, glass, and anything else gets processed so it can be reused or recycled properly. The leftover metal pieces, like the steel parts, are shipped off to metal processing plants. There, they get melted down and eventually used to make brand new products. Remember those magnetic separators? They are super effective at pulling out iron and steel, which then get sent off to be melted down. The plastic parts get shredded into smaller pieces and then usually compressed into dense bales or blocks. These bales can then be shipped to specialized factories where they will be used to make new plastic items, or they might become part of the raw material mix for new appliances or other tech gadgets. If the washing machine had any glass parts, maybe in the door window, that glass gets cleaned really well to remove any gunk, and then it can be melted down to make new glass products. Any leftover materials that cannot really be recycled, maybe certain kinds of rubber or complex mixtures of stuff, usually end up getting sent for final disposal, often meaning they go to specially designed landfills. These kinds of sorting and recycling setups drastically cut down on the amount of waste that just gets dumped in landfills. Plus, they help get valuable raw materials back into the economy so they can be used again. Sometimes, especially for really tricky materials, they have to use more advanced techniques, like thermal decomposition, which uses heat or special chemical treatments. These methods come into play for stuff that is hard to separate just by shredding and sorting mechanically, or for materials that need extra processing to make sure they do not cause pollution or release harmful substances. Good examples are certain plastic components that have other materials embedded in them, like plastic with metal pieces fused inside or attached rubber seals. Materials like these often cannot be sorted easily using the standard methods, so they need special treatment to break them down and separate the different parts. Rubber parts, particularly those made with complex chemical additives, are often tough to recycle effectively because of their complicated structure. For materials like that, processes like thermal decomposition or other chemical methods might be used. The goal is to basically unzip them into simpler building blocks that can potentially be reused or at least disposed of more safely. In situations where the appliance contains hazardous stuff, think mercury in old switches, or maybe some types of batteries or old lighting components, those materials absolutely have to be handled with special procedures. This might involve a chemical process designed to neutralize the dangerous parts, or maybe one that locks them up safely so they can be disposed of without causing harm. Materials like polyurethane or polyester, which you often find used as insulation around wires or in various other parts inside appliances, might also be treated with thermal decomposition. This helps break them down into simpler substances that could potentially be recycled. And then you have situations where washing machines or other electronics contain complex composite materials, stuff made of several layers of different materials bonded together, like plastic fused with metal layers or reinforced with fibers. These often require very specialized processing to carefully separate the layers so that each material can hopefully be recycled on its own. Overall, the reason for using all these different technologies is to make the whole disposal process as efficient as possible and to minimize the harm done to the environment. Because if these materials are not handled the right way, you could end up with pollution or dangerous chemicals leaking out into the ground or water. Did you know there used to be a rodent the size of a large dog living back in prehistoric times right alongside saber-toothed tigers? And today, it soaks in hot springs with tourists in Japan and can cost up to $5,000 each. That is the capybara. Its meat is officially recognized as fish for Catholics during Lent, and its skin is a favorite among luxury brands. So how did a meme animal turn into a farming business, a delicacy, and even a pet? Here is the full story of capybaras, from the wild to VIP farms and $1,000 wallets. Capybaras are not just internet stars. They are also raised on specialized farms. The largest number of these farms are found in South America, especially in Brazil, Venezuela, Argentina, and Colombia. Capybaras have been around for millions of years. Their ancestors were even bigger and possibly lived alongside giant sloths and saber-toothed tigers. The earliest capybaras appeared in South America around 30 million years ago. Back then, in the area of what is now Brazil and Argentina, there were giant rodents from the same family, like Joseph-Wartegacia monesi. That creature could grow to over 10 feet long and weigh more than 1,500 pounds. Experts believe it looked like a modern capybara, only it was the size of a cow. So how did capybaras adapt to life near water? They developed some incredible traits that helped them survive. Their webbed feet make it easy to swim and walk through swampy areas. Their eyes, nostrils, and ears sit high on their heads, just like hippos, so they can breathe and watch what is going on while staying mostly underwater. And they have a special thermoregulation system. Capybara skin helps them maintain an ideal temperature even in hot climates. Archaeologists have found capybara bones in ancient native settlements across South America. Tribes living along the Amazon hunted them for meat and hides. Some tribes even saw them as sacred animals because they could live between two worlds, both on land and in water. When Spanish conquistadors arrived in South America in the 16th century, they noticed right away that the locals ate capybaras. But that raised a question: can you eat them during Lent? The Catholic Church banned eating meat from mammals during Lent, but fish was allowed, so Spanish missionaries asked the Vatican for a ruling. After long discussions, the priests decided that, since capybaras spend most of their time in the water, they could be considered fish. That is how capybara meat was officially approved for Lent, and the tradition still exists today in parts of Venezuela and Colombia. Even though capybaras are hunted for their meat and hides, they are not an endangered species. Today, they can be found not only in South America, but also in zoos, private reserves, and even as pets in many countries around the world. Capybaras are living proof that nature creates perfect survivors. From prehistoric times to internet memes, they are still one of the most unique rodents on the planet. Capybara farms look a lot like nature reserves, large areas with green meadows and man-made ponds, because capybaras absolutely love water. Commercial farms and nature-style reserves can cover 50 or even 100 acres or more. Trees provide shady spots where capybaras can relax. There are 3 main reasons to raise capybaras. First, for ecotourism. Some farms let visitors pet, feed, and even swim with them. Capybaras have charmed people for a long time with their calm personalities, and farms focused on ecotourism offer amazing ways to connect with them. Visitors can not only watch the animals, but also feed them, pet them, and swim right beside them. These farms usually have wide open spaces with water areas, grassy fields, and shaded zones. Since capybaras spend up to 80% of their time in the water, they are given large ponds about 3 to 5 feet deep, perfect for swimming with tourists. Most farms offer feeding sessions where visitors can buy special snack kits that include fresh greens, vegetables, and fruits. The average cost for one portion ranges from $3 to $5. Feeding helps capybaras get used to people quickly, and they often come right up to the guests. One of the most popular activities is swimming together. The water must be comfortable for the animals, around 80 degrees Fahrenheit. For safety, some farms only allow swimming with young capybaras under 2 years old, or with adult ones that are already used to human contact. In the United States, Brazil, and Japan, the cost of visiting a capybara farm ranges from $10 to $50 per session, depending on the length of the visit and activities offered. Some farms even offer VIP tours for $100 or $200, which include private photo shoots and special treat packages. These places are getting more and more popular, especially thanks to viral capybara videos on social media. In Japan, for example, some farms even build hot springs, where tourists come just to watch capybaras enjoying warm water in the winter. The second reason capybaras are raised on farms is to sell them as pets. Demand for capybaras as household pets is growing, especially in the United States and Japan. People love them for their chill vibe, high social skills, and cute appearance. They get along well with people and other animals, especially if they are raised together. In the United States, the average price of a capybara from a specialized farm or breeder ranges from $1,000 to $5,000 per animal. However, the price depends heavily on documentation, health, and the age of the animal. On top of the purchase cost, owners must also budget for a large enclosure and pool, special food, and vet care. Capybaras are not apartment-friendly pets. They need plenty of space and access to water. Plus, they are social animals and do not do well alone. That is why experts recommend keeping at least 2. Is it even legal? You might be asking. Well, it depends on the state. In Texas and Pennsylvania, it is totally legal with no restrictions. In New York and Florida, you need a license to keep one. In California and Georgia, capybaras are strictly banned. In Japan, capybaras are super popular because of anime and social media. But owning them comes with even stricter rules. Capybaras form close bonds with their humans, love cuddles, and can even learn to respond to their names. But they are not like dogs. You cannot train them easily, and if they get bored, they might chew on furniture or walls. In South America, especially Venezuela, Colombia, Brazil, and Argentina, capybaras have traditionally been raised for meat and leather. Their meat is considered a delicacy, and their hides are used to make premium products. Despite local traditions, many international environmental groups are against large-scale farming of capybaras. Some countries have already banned or limited the sale of their meat to protect wild populations. In Peru and Bolivia, hunting capybaras commercially is illegal. In Europe and the United States, importing their meat or hides is tightly regulated. Still, capybaras are raised for meat and leather. So let us take a closer look at how that works. Capybara meat is often described as tasting somewhere between pork and rabbit. It is rich in protein and low in fat, making it popular among fans of healthy eating. The price of capybara meat depends on the country and region. In Venezuela, the average cost of 1 pound of meat ranges from $5 to $10, while in Brazil, it can go up to $20 due to limited supply. Capybara leather is soft, flexible, and incredibly durable. It is used to make high-end accessories like belts, wallets, handbags, and boots. Since it is a rare material, luxury brands really value it. For example, a belt made from capybara leather might cost $200 or even $500, and a handbag could go for more than $1,000. On these farms, capybaras grow up in semi-wild conditions. When they are raised for meat, young males aged between 12 and 18 months are selected. At that age, they usually weigh about 140 pounds. They are then captured and taken to specialized slaughterhouses. In Venezuela and Brazil, there are strict humane slaughter laws. Animals must be killed quickly and painlessly, usually by electric shock or firearm. Afterward, the carcass is processed, the hide is removed, and the meat goes through veterinary inspection. The hides are cleaned, dried, and sent to leather factories where they are tanned and turned into materials for belts, wallets, and more. Capybara breeding on farms happens under controlled conditions, but mimics nature as much as possible. Since capybaras are social animals, they live in groups with one male for several females. Females are ready to reproduce by the age of 10 or 12 months. Males take a bit longer, around 15 to 18 months. Mating happens in water. Males compete for females, making signature sounds and chasing them around. A capybara pregnancy lasts about 5 months. Usually, 3 to 5 babies are born at a time, but sometimes there can be as many as 8. The mother feeds her babies milk for the first 4 months, but by the end of the first week, they are already nibbling on solid food, grass, veggies, and grains. Farmers closely monitor the process, choosing the healthiest animals for reproduction. To avoid inbreeding, they regularly switch out males between groups or buy new ones. Under good conditions, a capybara population can double in just 1 year. That is because one female can give birth to 15 or even 20 babies over her lifetime, so farms can quickly grow their numbers if there is demand. Capybaras live about 10 years in the wild, but on farms or in captivity, they can live up to 14 years, thanks to better food, medical care, and no predators. In the wild, capybaras are often hunted by jaguars, anacondas, caimans, and humans, which greatly shortens their lifespan.